by Jamal Belazoglu, Qin Zhang, and Qinlu Lidezo.
Thanks for the introduction. So, morning, everyone. So, this is joint work with Jamal Belazoglu, who is in Cyrus, Algeria. So, I guess you all know at distance. So, it's basically the minimum number of insertion, deletion, and substitution you can transfer as the string S to string T. Okay. So it's a basic question. So this is an example. So for banana, ananas, and the added distance is 2. So it's a basic question. It has a lot of applications. For example, it's a very important question in bioinformatics because we want to measure the similarity between DNA sequences. So it can be used for automatic spell checking. So today we are going to study the threshold version of the added distance. So let's assume the alphabet size is 2. And we are given a threshold k. So if the distance is less than k, so we are going to compute the distance exactly and output all the edits. If the distance is larger than k, we just output error. So this is useful in practice because in practice people usually care about those similar pairs. If the distance is large, if we know that distance is large, then we don't care about the details. Okay? So we studied the problem in a few settings. So the first model is the one-way communication model. It's called the document exchange. It has a set of applications. So here we have Alice and Bob. Alice says string S, Bob has string T. So what Alice do is to compute a kind of sketch of the S, to send this message to the Bob, and Bob computes the added distance of S and T based on this message and his input T. Okay? And the second model is called the simultaneous communication model or sketching. So here we also have Alice and Bob. So they compute a sketch of their strings and send it to a third-party referee. And then referee, after getting this to sketch, want to solve this threshold problem. So this is useful in applications like similarity join. So this is important, a very important question in database. So if we have a sketching algorithm, what we can do is, so the problem is like let's say we have a set of DNA sequences. We want to find those similar pairs. Okay? So if we have a sketching algorithm, then we can first pre-processing each of the string in parallel. And then we compute the sketch of all the strings and then send it to a central server, for example. And then the server can compute, find those pairs based on those sketches. So why this is useful? Because we can actually compute distance much faster on the sketches compared with compute distance on the original string. You will see later. Okay. So and the third model is streaming model. So here we can basically we can scan the string S from left to right once, then scan the string T from left to right. Then using a small space, we want to compute their distance. Okay. Again, for the threshold model. Okay. So these are 3 problems we're going to talk about in this talk. So here's like set of results. So this document exchange has been actually studied for decades. So a lot of previous results. So what we get is almost information theoretical optimal communication for when k is kind of small, and the time we use, the encoding decoding time we use is linear. Encoding means Alice compute the time to compute a sketch of S, and decoding time is like for Bob to actually compute the distance based on his message and his input. Okay, and for sketching, we don't know much previous work. So this is the first sketching algorithm has poly k log n size. And previously, if we want the sketching to be linear, then so there's a linear lower bound. Basically, even like you want to differentiate if the distance is at the most 2 or more than 4. So you have to like basically keep the whole string in the sketch. Okay. So this is a paper by Adoni et al. A few years ago. And for streaming, so this is actually like a direct kind of follow-up of the sketching algorithm because we can construct the sketching in one pass. So we get a streaming algorithm too. So the same basically space is basically the size of the sketch. And the final problem is called simultaneous streaming. So where we can actually scan the 2 strings simultaneously in a coordinated fashion. And if we can do this, instead of like scan one then the other, if we can do this, we only need this amount of space. So so it's k log n. So this is basic like space-efficient dynamic programming. It's kind of easy compared with the other results. Okay. So today I will focus on the document exchange and the sketching result. Okay. So I want to highlight this result because we are going to use this as a black box. So we named this IMS scheme. So named after the last name, the initial of the authors. So just remember this bound. We are going to use this as a black box. Okay. So before talking about our results, we want to first introduce our main tool. We named the CGK embedding. So this is a scheme proposed by Chakrabarty, Goldenberg, and Chkolky fairly recently, and a similar idea also was proposed by Saha. So this embedding is a mapping from n-bit string to 3 n-bit string. So it's fairly simple. So we maintain two counters, I and j. I is for the input string, j is for the output string. So we proceed by steps. So at each step, we first copy this bit to the output string. And then we flip a coin with half probability. We increment I, otherwise we just keep the I. And then we stop if I reach the end of the string. And every step we increment j. So we copy this and then flip coin to see if we want to move this I to the next position, but we always move j forwards. So when I reach n plus 1, because of this concentration bound, so j, very likely j will be less than 3n. So if it's less than 3n, we just pad 0. Okay, so that's the whole embedding. It has very good property. It's a very nice embedding. It's a weak embedding, by the way. So if we can show if the distance between st is k, then after embedding in the Hamming space, the Hamming distance of fs and ft is between k and k squared. So the distortion of the embedding is basically k. Okay, so this is a nice property we are going to use. So if we do this on the two strings simultaneously, we can actually view this embedding as a random walk on two strings. So if we just look at this is shift between the two counters. One is for S and the other is Q. So J is actually shared by the two strings. So if we look at the shift of P, the basic difference between P and Q, it's actually a random walk centered at the origin. It's like a simple random walk, but sometimes it will stay at the same place instead of move to left or right. But if they move, it will go left or right with equal probability. Okay, so this is a nice thing too. Okay, so let's start to discuss our result. So because I want to make it simple, so I will cheat in multiple places. So if you have questions, just ask. Okay. So the main idea is actually very simple. So for document exchange, if we know like where the edits actually occurs, it can make the problem much easier, right? So if we know like roughly where other k edits are located, so the idea is if we can find k pairs of blocks of size at the most k to the power 99 that they contains all the edits, then we can just plug in this IMS scheme because IMS scheme gives something bound like this, so it will give this bound. This is basically our result. I mean, you have a log n factor, but that's something else. Okay. So this is the main idea where we start. Okay. The question is, of course, how to identify those neighborhood pairs where the edits are located. Right. So here's like the overall as a general kind of high-level idea. So we first try to do the CGK embedding to try to think the problem in the Hamming space. And then we can, if we get this S prime and T prime, it's two string in the Hamming space, we do random partition into two blocks. And then we do error correcting code for Hamming distance with respect to those blocks. And then we do the reverse embedding. So that's like a high-level idea. Things here, in Hamming space, things are always nice. So we can do random partition because they are aligned perfectly. Right? So the challenge is if we do this, because CGK embedding will, if the added distance of S and T is k, it will give up to k square errors. And those k square errors will be distributed actually to remote places, to k square pairs of blocks because of periods. So they will spread out. And that will introduce the effect of k square, which is something we don't want. So we want something like k times some log factor. Okay. So this is the difficulty. So what we show is we can actually reduce this k squared to k if we can remove those long common periodic substrings. So this is actually a fairly technical step because it's not easy because everything has to be done in a one-way communication. So they have common long common periodic string, but Alice has to actually remove those without talking to Bob. Okay, so this is why this is difficult. Without talking to Bob, how can we remove these things? But this is fairly actually we can. So if we have time, we will talk about this a little bit more. But it's a bit complicated. So it's not that. So it's not the most important thing, but it's kind of technical stuff. So I choose to skip it because of time. Okay. All right. So let me give you like a high-level idea of our approach. So recall that we can think the CGK embedding as a random walk. So we call a walk step from state PQ a progress step if these two bits are different, and one of these cases happens means at least one of the P and one of the two counters increments. So we call this is like a progress step. Okay. And we call a sequence of sequence of work the progress phase. So we start from somewhere a state one progress step happens, then to the first state that basically this is the eddy distance of the tail of the two strings decreased by 1. So we call like this like moving this random walk the set of this random walk steps progress phase. Okay, start from some state that one progress step happens, then to some point that the eddy distance of the tail strings decreased by 1. Okay. So why we want to introduce these concepts because a progress phase actually corresponds to a pair of mismatching blocks. Okay. And obviously we can have at the most k progress phases because the ED of the original strings are bounded by k. Otherwise we can detect. Okay. So we have at the most k pairs of mismatching blocks. And the size of the mismatching blocks actually corresponds to the number of random walk steps in each progress phase. This is how we relate these things and go back to the main idea. Okay. So this is just a copy of what we have said. So we can show that with high probability, a progress phase consumes at the most k to the power of 10. This value, this number is something arbitrary, progress steps. And this is the important part. If we can show if we can, after properly removing those long common periods, we get a progress step in at most k to the power 50 random walk steps. So if we multiply these two things together, so basically shows the size of the mismatching block is bounded by k to the power 99. And because we have at the most k progress phase, so we can have at least k pairs of blocks that differs. Okay. And this gives, then we plug in IMS, then it gives k log k squared. And other steps cost k log n. This is something like you cannot break because this is like information theoretical bounds. Okay, so that's basically the proof of, it's very high level for document exchange. Okay. All right, good. So let's move to the sketching. So I hope you still remember the problem. So we have S and T. So each of them want to compute a sketch of a string and send to referee. Referee, based on these two sketches, compute the distance if it's at the most k, otherwise output error. Right. So the idea is we can view alignment between ST as a non-crossing bipartite matching. So let's say this is the alignment. So these edges corresponds to a pair that can be matched. Those singleton nodes correspond to those insertion, deletion, and substitution. Right. So we can actually compress this alignment by writing down all the singletons and the starting, ending edges of each cluster. So we don't care about those things. So this is like consecutive edges. So we can just write down the first and the last edge. We don't need to record those intermediate edges. Okay. So we denote this is like a sketch. Probably should write a summary of alignment or sketch of the element. Okay? So if we think about the optimal solution, if there are distances at most k, if we think about the optimal solution, actually we can, the sketch of the optimal solution is k log n. Okay, because the optimal solution has at the most k edits, so we have at the most 2k singletons, right? So, and then number of edge cluster is also bounded by k. Okay. So this is kind of the so this is some notation. So give a set of alignments. Let this I to be the intersection of those alignments. Means the if edge belongs to I, if and only if the edge belongs to all the alignments, all the non-crossing bipartite matching. Okay. So this is the main idea. So if there exists optimal alignment that goes through all the edges in I, then we can kind of reconstruct the optimal alignment using the sketch of those alignments. Here, this I actually can be empty. We don't care because at the end we will reconstruct stuff from those sketches, not from I. I can be empty. So if I is empty, actually it's a simple case. So this is something, of course, we need to give a proof, but because of time, we'll skip the proof. But this is the main idea. It's like a lemma. So basically, taking intersection, if there's an optimal alignment that goes through all the intersections, then we can reconstruct optimal alignments using those sketches of those set of alignments. So far, nothing related to random walk. So here's how we connect this idea to random walks, to CGK embedding. So we can view the random walks, the sequence of states, P1, Q1, P2, Q2. So we just record those state of counters at each step. This actually contains the alignment, not necessarily optimal, but it contains alignment. Can be constructed in greedy way, and the sketch of this alignment is actually can be bounded by poly k log n. This is because of the low distortion of CGK embedding. Okay. So here's the key lemma, so key technical lemma. So if we take this amount of random walk and each of them give alignments, then we can show that with high probability there must be optimal alignment that contains the intersection of those elements generated by random walks. Okay. And so this is actually gives the sketch size. Basically, we have each kind of sketch of this. The sketch size of each alignment is bounded by poly k log n, and we have this amount of this. So multiply together, this is actually the final size of the sketch. Okay? So this sketch actually can be reconstructed at the referee side because this actually corresponds to the difference of S prime and T prime. This is like after CGK embedding of the original strings in the Hamming space, and for Hamming sketching, we know how to do it. And we need some additional structure to kind of do reverse mapping, go back to the edited space to find all the edits, but that's kind of something, yeah, sure. So just some cleanup step. Okay. So that's basically everything about sketching. Okay. So just conclusion. So what do we have? Upturn is kind of information theoretical optimal. Result for small k with almost a linear encoding decoding time for document exchange. And for streaming the sketching, we get the first poly k log n size of space result. Okay. There are a few open problems. So first of all, like can we do for document exchange, can we get this bound for all k instead of just for small k? And second is, so here like this sketch size now is kind of a bit high. It's k to the power 8. I think with some more careful, we were just lazy. Like when do the analysis, we use a lot of crude union bounds. So we actually can reduce it to, I'm pretty sure we can reduce it to k to the power 4 log n to the cube. Or maybe this is something I'm not entirely sure. But can we get, for example, k square log n, for example? Or maybe some higher lower bounds exist. We don't know how to prove lower bounds in this sense. And the final question is it possible to de-randomize our algorithm? This is useful because it will give us better error correct code for at distance. Okay, so I guess that's all. Thank you.
Question?
So you mentioned this linear lower bound for sketching at distance, right?
Yeah.
So which field is this for? Is it for finite field or for real?
It's probably a question for Alex.
For real, so some theory of that.
Yeah, this is something I'm thinking about right now. I feel there's some difficulty actually. I can talk to you. Yeah, it's probably not that easy. I'm thinking about this these days. Because of periods, again, like this error will be spread out, and you have no way to actually detect, and it's messy. So because of the periods, you distribute the error to multiple remote places. And it's hard to differentiate the k and the k square, even if, because for approximation, your target is probably like a much small space or sketch size, right? So if you use much small sketch size, then it's hard to differentiate the k and the k square. Yeah, we can talk later. I mean, I don't have any concrete yes or no.